So as promised, Year 10, here is a quick run through of the homework that I set you a couple of weeks ago about the energy change for reaction for chlorine gas and ethane gas. Okay, so just to remind you, the first slide here is showing you some of these numbers. You might want to make a note of some of these because I'm going to be referring to those in a minute. So these numbers here, these bond energies, you've got it on your sheet. CH4 is 412, CC 368, ClCl 243, HCl 432, and CCl 346. So we're going to use those numbers to work out the energy change for the reaction. Now, the first part of the reaction asks you to write a balanced equation to express this using chemical formulae. Now, I did show you this on the board, and I did promise to put it on to show my homework. I don't think I did in the end, but I guess it's fairly simple to look it up if you didn't remember what I'd shown you on the board. Okay, but this is ethane. Okay, you haven't done this yet, but later on in year 11, when you've done the organic chemistry, you will get to know what ethane is very well. You spend a lot of time doing it. So it's C2H6 plus Cl2, so ClCl, okay, which is going to be producing HCl and chloroethane. So it gave you that in the question, and actually you could look these formulae up if you like. Now, my first step on each of these, as I told you in the lesson, is always to draw out my nice expanded formulae so I can see all of my bonds. Okay, so what's happened in this case is that I've got C2H6 with chlorine. And what happens is I'm effectively breaking this apart, and then I'm joining one with this here and the other one with the hydrogen that has come off here. Okay, so what you can do to work out, it says calculate the energy required to break all of the bonds in 1 mole of reactants. Okay, it says 1 mole because it's in kilojoules per mole. These things are always given in 1 kilojoules per mole. So to break all of the bonds, you're going to have to break 1, 2, 3, 4, 5, 6 CH bonds. You're going to have to break 1 C bond, and you're going to break 1 Cl bond. Okay, so we are going to then add up how much that is. Okay, so that's 4 times 412. Okay, that is given to you. CC is 368 and ClCl is 243. So you just add those together, and that should give you 3083, I think, off the top of my head. So that's to break all those bonds. So we're going to make them all in the next step, which will be on the next slide. Right, so just transferred onto the next slide. So here we are. We've got the nice little equation at the top here to help you again. So we are breaking. That's how many we broke. That was the part 2 of the question. So it says calculate the energy released in the formation of all the bonds in the products. Okay, so we're going to do the same sort of thing. We're going to look at, we say we form in the products, we form 1, 2, 3, 4, 5 CH bonds. Okay, we are going to form 1 C bond. We are going to form 1 CCl bond. Okay, and don't forget that we've also formed 1 HCl bond. Okay, so this will be 5 times 412. That is 368 from the table. This is 346 from the table, and this is 432. So you add all these together, and it comes to 3206. Now, question is which one of these is positive and which one of these is negative? Right. So when I remind you, when we thought about those little Molly-Mod models, you know, little plastic models that we made, and I said that when you break a bond, you've got to put in energy. Okay, so to pull those two molecules apart, I had to put in energy. Okay, so breaking bonds is always positive, okay, because you put in energy to break the bond. Now, making a bond is the opposite. Okay, so making the bond is always going to be negative. Okay, so the energy released in the formation of all the bonds is minus 3206. That's question 3. So to answer question 4, we need to find out whether it's overall endothermic or exothermic. What's the total energy transfer? Okay, so you add 3083 and you minus 3206. Okay, so it comes out at minus, I think, 123 kilojoules per mole. Now, you should know that if it's negative, it is exothermic, because we did talk about that, but I'll show you in an energy level diagram, or what they've called a reaction profile. We will talk about why that's the case. Okay, so we'll make sure that you understand why that is on the next slide. So on the energy profile, I'm doing question 6, I'll come back to question 5 in a minute. What it's showing you is effectively that your reactants had a higher energy, okay, and that to get to your products, they are losing 123 kilojoules per mole. So this is your reactant, this is your product. Okay, so this is a minus. So this is exothermic, remember, because if you've got more chemical energy in your reactants than you've got in products, that chemical energy is coming out of your chemicals and it has to go somewhere. Now, the place it goes, remember, is heat. So this is going to give out heat energy, so it's going to get hot, so it's going to be exothermic. Now, it also says about activation energy and energy transfer. So for the moment, I'm just going to draw a little activation energy hump. Okay, so we're going to talk about the activation energy hump in a minute, because this document asks you to give a value for the activation energy. And I think it's teaching you something that is misteaching you something that you'll have to unlearn in A-level chemistry. So I'm a little bit unhappy about this question, but I will talk to you about what they expected and what I think is the real answer. But then we'll go on to question 5 next. So question 5 was actually taking you back to this picture and actually thinking about what does it actually mean. Okay, so the differences between the reactants and the products. Now, ultimately, I know that we broke all of this up into individual atoms, but actually the only things that have changed are we've swapped one of these for one of these, and we've swapped this for this. So to an extent, all we've done is we've broken this bond here and this bond here, and we've made this new bond here, we made this new bond here. If you look at everything else has stayed the same. So this unit here has remained the same throughout the reaction. So what you could have done is, what you could have said is that your bond breaking is going to be a CH, which is 412, plus a Cl-Cl bond, which is 243. So that'd be 655. Okay, and your making is going to be a CCl bond, which is 346, plus an HCl bond, which is 432. Okay, which will give me 87778. Okay, so remember we said that this is positive because we've got to put energy in to break bonds. This is negative, could get energy out making bonds. Now, if you do that same calculation and do for the whole thing, delta H equals 655 minus 778. You notice, magically this also equals minus 123. Now, isn't that neat? Okay, so you don't actually need to break everything up into individual atoms. Now, my answer sheet suggests that the activation energy for this is equal to all of this, okay, because I told you about activation energy is about breaking bonds, okay, to get a reaction started. Now, I'm not 100% sure I really like this question, but I guess they're trying to illustrate a point in that an activation energy is about breaking bonds. But those of you who want to go on to do A-level chemistry, what you actually learn is that this thing breaks up. Okay, so chlorine has some UV light coming down on it. This is beyond what you need to know, by the way, which breaks it up into individual chlorine atoms. Okay, so you remember a chlorine atom will have 7 electrons around the outside. So it's got an unpaired electron. It doesn't like being on its own. It'd rather join up. So it's very reactive. So what actually happens, this chlorine radical will kind of bond across here like this, okay, and it will make a kind of intermediate, okay, so there'll be like the activation energy is actually slightly lower and more around what the strength of this bond is, okay, because then there'll be a reaction intermediate and then this will start to kind of split apart. So that's way more than you need to know, but just bear in mind that these things aren't always as simple as the GCSE makes out. Anyway, I'm going to put you up on the final slide. I'll show you the mark scheme so you can see the official mark scheme for this. But if you've managed to work out delta H, so if you managed to work out all of the breaking, all of the making, either on this version or the other, you've managed to add it together and get -1, 2, 3 and set its exothermic and draw a reaction profile, or an energy level diagram as I also call them, then you are doing just A-OK on this topic. And just finally, here is the mark scheme officially if you need it. So there we go, so you can have a look through, pause it if you need.